This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Today's discussion centers on the research paper LMS AUTOTSF, Learnable Multi-Scale Decomposition and Integrated Autocorrelation for Time Series Forecasting. This paper proposes a novel architecture for time series forecasting. Let's start with the core problem the authors are addressing. What are the limitations of existing time series forecasting methods that motivated this work?
Existing methods often struggle with the complexity of real-world time series data. Traditional approaches rely on predefined trend and seasonal components, which may not accurately capture the dynamic nature of many datasets. Furthermore, capturing long-term dependencies and fine-grained patterns simultaneously remains a challenge. Many existing models are computationally expensive, hindering their applicability to large-scale datasets or real-time applications.
The paper introduces LMS AUTOTSF. Can you describe the key architectural innovations of this model?
LMS AUTOTSF addresses these limitations through a multi-pronged approach. First, it employs a learnable multi-scale decomposition. Instead of predefined components, it uses two separate encoders per scale, one for low-pass filtering trends and one for high-pass filtering seasonality. These filters are learned directly from the data, adapting to the specific characteristics of each time series.
The learnable aspect is crucial. How does this differ from traditional methods, and what are the advantages?
Traditional methods often assume fixed trend and seasonal patterns, which might not hold true for all datasets. LMS AUTOTSF's learnable filters allow the model to dynamically adapt to the underlying patterns in the data, leading to more accurate decomposition and improved forecasting accuracy. This adaptability enhances the model's generalizability across diverse datasets.
Beyond the learnable decomposition, what other novel elements does LMS AUTOTSF incorporate?
A key innovation is the integration of autocorrelation. The model computes lag differences in time steps, explicitly incorporating temporal dependencies into the forecasting process. This allows the model to better capture the relationships between past and future values. The architecture also uses a multi-scale approach, processing the input at multiple resolutions to capture both local and global patterns.
The paper mentions the use of fully connected layers. How do these layers contribute to the model's performance?
Fully connected layers are used for both temporal and channel processing within each encoder module. The temporal processing layer handles the sequential nature of the time series, while the channel processing layer captures interactions between different features. This combination allows the model to effectively handle both temporal and cross-feature dependencies.
The authors claim LMS AUTOTSF is computationally efficient. Can you elaborate on this aspect?
The lightweight design, based on fully connected layers rather than more complex architectures like recurrent neural networks or transformers, contributes significantly to its computational efficiency. Experimental results demonstrate faster processing times compared to state-of-the-art methods, while maintaining or even improving forecasting accuracy.
What data sets were used to evaluate LMS AUTOTSF, and what were the key performance metrics?
The evaluation involved 8 widely used benchmark datasets, including weather, electricity, traffic, exchange, and 4 ETT datasets, covering various domains and complexities. The PMS dataset, focusing on short-term traffic flow forecasting, provided an additional challenge. The M4 dataset, with its 100,000 time series, offered a comprehensive benchmark. Performance was assessed using MSE, MAE, SMAE, MATE, MACE, and OWA, providing a comprehensive evaluation across different datasets and forecasting horizons.
How did LMS AUTOTSF perform compared to other state-of-the-art models?
LMS AUTOTSF consistently outperformed state-of-the-art models like Time Mixer, iTransformer, and Patch TST across most datasets and forecasting horizons, particularly in high-dimensional time series forecasting. In short-term forecasting, it showed competitive performance with Time Mixer, surpassing other models.
The paper includes an ablation study. What insights did this study provide?
The ablation study investigated the individual contributions of learnable decomposition and autocorrelation. Results showed that both components significantly improved performance, with the combination yielding the best results. This highlights the importance of both dynamic decomposition and the explicit incorporation of temporal dependencies.
The paper mentions the use of FFT for frequency domain transformation. Can you explain the role of FFT in the context of LMS AUTOTSF?
The fast Fourier transform, FFT, is used to efficiently transform the time series data from the time domain to the frequency domain. This allows the model to operate on the frequency components of the data, enabling the learnable low-pass and high-pass filters to effectively separate trend and seasonal components. The inverse FFT then transforms the filtered components back to the time domain.
What are the limitations of LMS AUTOTSF, if any? Are there any specific types of time series where it might not perform as well?
While LMS AUTOTSF demonstrates strong performance across a range of datasets, its effectiveness might be limited by the complexity of the underlying patterns in the time series. Extremely noisy data or time series with highly irregular or non-stationary patterns could pose challenges. Further research could explore ways to enhance the model's robustness to such complexities.
What are the potential future research directions stemming from this work?
Future work could focus on extending LMS AUTO-TSF to handle even larger scale datasets and more complex time series patterns. Exploring different filter designs and incorporating advanced attention mechanisms could further improve performance. Investigating the model's ability to handle missing data or outliers is also a promising avenue for future research.
In summary, LMS AUTOTSF offers a compelling approach to time series forecasting, combining learnable decomposition, autocorrelation, and multi-scale processing for improved accuracy and efficiency. Thank you for this detailed discussion.